Hello. We will be presenting on behalf of the Prosthetic Compatibility device team within the HSTEM enterprise. I am Mason Steele.
I'm Kelsey Jensen.
And I'm Koty Shetler.
Annually, 150,000 people undergo below-the-knee amputations. And for those individuals that choose to pursue a prosthetic device, a number of challenges are posed to them, such as a high cost and an issue of comfort.
Our problem statement is to develop, design, and test a device concept that improves the fitting process in below-the-knee amputees to reduce pain and friction resulting from a prosthesis. Our goal is to develop a proof of concept device that can be used in further application-based development of this technology. Our requirements include having an informative output, make the device adaptable for improvement, allowing for long-term data collection, and also making the device reusable.
A look into our general design concept. The device must be a wearable device that can be worn over the amputation site of the individual. It also must be such that, as an all-in-one device, it can characterize the topology of the amputation site as well as the pressure over the area of the amputation site. As such, the device must also measure the internal deformation of the device to determine the topology of the amputation site, as well as be able to measure the force of the stump against the prosthetic device to extrapolate pressure information. A further look into our design concept as an application, we chose to pursue a fabric sleeve design, as well as utilizing capacitive stretch sensors and resistive force sensors. The fabric sleeve design allows for adequate flexibility as well as the ability to create anchor points through sewing. Lastly, the capacitive stretch sensor allows benefits such as the low ability to plastically deform and a high accuracy.
Here's our stretch sensor development. Our methods include fabricating the sensors using 2 sheets of conductive fabric with a silicone dielectric layer in between, creating the capacitor. Before curing the silicone between the 2 fabric layers, we pre-soaked the fabric to prevent textile leaking and to create a consistent silicone thickness. Each sample was measured to ensure the correct height of the silicone. These samples were cut out using a laser cutting machine for precise dimensions. Each sensor was constructed by securing a wire on the sensor, and our testing included creating a simple circuit array to measure the capacitance of the sensors, and then we also anticipate MTS testing to measure the resistance, stress, and load on the sensor.
On the electronic side of this project, the stream of data goes from the sensors to the driver boards to a main controller board where the data can then be processed. Newer updated sensor driver circuits were designed and then fabricated as custom PCBs that will then function to gather the force and capacitance data. Initial programming has been done to simply gather basic results and in the future lead to more specific data that can be used for the final project. In the fall, complete basic prototype should be nearing completion, where then, in future semesters, they can focus on more rigorous testing and optimization to create a more official device. We'd like to give thanks to all the professors, departments, companies, and postdoc students that helped us during the length of this project.